So yeah, it's my pleasure to introduce the second speaker of this session. Is Krijn Reijnders, and this is a joint work between Simona and Monica from Radboud University. So please, Krijn. Thank you.
Yes. So I'm Krijn Reijnders. I'm presenting today about cryptography using the Matrix Code Equivalence. And from this, we hope to make perhaps a post-quantum cryptographic group action. And I have to thank Eduardo because this morning he already gave a talk that covers quite a lot of what I'm going to discuss, namely code equivalence and how they made a cryptographic group action called, I made a scheme called less out of this group action. The code equivalence talk of this morning was mostly focused on the Hamming metric. And then the obvious first question that you have is, okay, what if you do it in a different metric, such as maybe the rank metric? Or you can also do it on more esoteric metrics maybe, but let's start with the rank metric. And indeed, so this is mostly based on joint work with my PhD supervisor, Simona Samajiska, and my colleague, Monika Krimoska. But also we discussed this cryptography part a bit more in this one. Yes. Okay, so what we will first discuss is what is matrix code equivalence, and in a one-liner you would say that it's if you have two k-dimensional codes of m times n matrices over some finite field, find an isometry mapping C to D. And then we will also discuss a cryptographic group action, which is a group action based on a cryptographically hard problem. And this is actually, if you have this, then it's a really great primitive. But actually only if computing this group action is efficient. So as Eduardo already mentioned, you also have this cryptographic group action in isogenies, for example, which is called C-side. That's a very good cryptographic group action, but it's not super efficient. And you can really see that this is a major drawback in isogeny-based crypto. So let's first discuss this hardness of matrix code equivalence and then see how it would work as a cryptographic group action. So what is a matrix code? Let's start out with that. Say you have these m times n matrices over a finite field, and you just take a subspace of all of these matrices. So a k-dimensional subspace, and then you give it the rank metric. A matrix has a certain rank, and then if you take the differences between the ranks of these certain matrices, this gives a distance. And then isometry is basically just a homomorphism between two of these codes, such that for every code word, the rank stays the same. And intuitively, this should make a lot of sense because what we're trying to analyze here, we're trying to analyze equivalence of two codes, and it shouldn't really matter if you permute certain columns or certain rows, or maybe if you add the first column to the last column, the information in this code basically stays the same. And we capture this with an isometry. As long as the rank of every code word stays the same, then for us, this intuitively feels like the same equivalent code. And so if we have two matrix codes, and we know they're both k-dimensional and they're both over FQ, can we find if such an isometry exists, or can we say that these codes are equivalent? This is a problem already posed in 2003, but we don't really know too much about the hardness of this problem. And that's the major part of our work, is analyzing the hardness of this matrix code equivalence problem. And then if we have that, then to build crypto from it. Now, what is known, and that's very nice, is that such an isometry between two of these codes can essentially be written as matrix multiplication on the left and on the right side by a matrix A or B applied to each code word. And that greatly simplifies this analysis already. So from a 2021 paper, there are some initial results on matrix code equivalence. This is a paper by Couvreur, Debris, Alazar, and Gabory. And they start out with this initial idea. We know that isometry maps C to ACB for every code word. And then this first point that they make is that either when A or B is trivial, then finding this isometry is easy. And this already has major implications for us in cryptography. Because in cryptography, we kind of want to use these vector rank codes quite often. But this immediately kills this idea. Because for vector rank codes, if you would add on the left by an invertible matrix, well, we have this FQM linearity already in vector rank codes. So this action is mostly trivial. And so the equivalence of vector rank codes reduces to this problem, which is easy. So code equivalence for vector rank codes we cannot really use. That's why we use these matrix rank codes. Then a second result is that we have is that this monomial equivalence problem, this co-equivalence problem in the Hammock metric, this reduces to MC as well. So this one is where what less is based on, of course. And then we get this sort of picture, where over here we have exactly these two problems discussed in this morning, this permutation equivalence and monomial equivalence, and also the reduction that was mentioned from graph isomorphism. And this paper already gave us that these also reduce to matrix code equivalence. This is a first suggestion that it may be also an interesting problem to analyze. Now I'm going to do something that maybe some of you won't like, because I'm also introducing a problem from multivariate crypto at a code-based crypto conference. Why do I do this? Well, there's another older result that reduces graph isomorphism to this quadratic maps linear equivalence, as we call it. And I will explain a bit more about it today. But the main result of our paper is actually that these two problems on the right, matrix code equivalence and quadratic maps linear equivalence, reduce to each other. And that will give us a very good starting point for cryptanalysis. So let's dive into quadratic maps linear equivalence. It's not such a hard problem, so we'll get through it. Take a system of multivariate polynomials, so just k of them, and each one is just in n variables, x1 up to xn. Now, in multivariate crypto, it's usually most interesting when the degree is at most 2. So you have that part of degree 2, and then a linear part and a constant part, and all of the coefficients are over the finite field. And actually, it's most interesting when it's even homogeneous, which is then it's very easy. Then it's just these gamma ij constants. And this already defines quadratic maps linear equivalence. Namely, say you have 2 of these k-tuples of these quadratic maps. Can you then find 2 matrices, S and T, such that first permuting all of the variables and then permuting the resulting polynomials that you get from it maps the first instance F into the second instance P. Now, you might wonder, how does this relate actually to these matrix codes? And this is also not too difficult, because these quadratic maps, you can see them as well as a matrix multiplication. So you take the variables, x1 up to xn as a vector, on both sides of this matrix in the middle that you make from these coefficients. And then we get that actually evaluating one of these polynomials in x is the same as multiplying on the left and on the right by x of this matrix. And then if we have this system of these k polynomials, well, if we map every such polynomial into a matrix, then we get k matrices. And these k matrices then span a matrix code. And the main idea is actually that if you turn a QMLE instance, where we had this P and F, into an instance of matrix codes, F and P, then you can play a bit with this and reduce one problem to the other, and vice versa. Although it's the main idea, I don't want to dive into too deeply over here because it's just a bit technical, and I want to get to the cryptography part here. But the main result is then that quadratic maps linear equivalence is already a well-known equivalence problem in multivariate crypto, and that we say actually matrix code equivalence is then equivalent to quadratic maps linear equivalence. And then the cool thing is that all of these algorithms we already had for quadratic maps linear equivalence, we can just start applying them to matrix code equivalence. And this gives a better upper bound to the complexity of solving matrix code equivalence. Mostly in this talk, I'll actually just assume that M is smaller than N, because otherwise we could take the transpose and we get the same result. And then we get a solvability in this complexity over here, whereas the previous complexity was q to the power m squared, which is basically brute forcing it, right? You either guess A or B, and then if you have the right guess, you get a matrix code right equivalence that you solve. Especially when the k, this dimension of your code, is smaller than n plus m, there in some sense there are then holes in your code, and we can even improve the complexity to q to the power m. Now, how are we going to use this in cryptography? Well, it's basically easy, right? We have a group reaction here. Mu maps C to ACB, And mu is then actually just a pair of matrices. So we could say that it acts on these codes. And so this group of matrices acts on the set of k-dimensional matrix codes. And so this is a group action. And we think it's cryptographically hard as we have this analysis, which makes it a cryptographic group action. And then we can start using it as a primitive, right? So how do we use this as a primitive? And Eduardo already touched on this, but this is just to repeat this idea of using cryptographic group actions a bit more because we think it's a good idea. Let's say we have two elements of the set and the group element that maps one into the other. Then how hard is it to find the group element that's basically this cryptographic primitive? And if this is hard, then how easily is it to make what can you do with it? You can make like a zero knowledge interactive proof of knowledge. And from such an interactive proof of knowledge, you can easily make an identification scheme and then a signature scheme, right? You apply the digital signature, you make a digital signature by applying fiat-Shamir. This is really common strategy actually for post-quantum signatures, and this is how they apply it in dilithium or MQDSS or PICNIC. And then these cryptographic group actions are also already part of the cryptographic landscape. For example, pattern signature scheme can be seen as such as basically this process, and then less FM. And in the isogeny space, you have this C side, which is a key exchange, and C sign, which is a signature scheme based on this idea. These last two are a bit different, of course, because as we mentioned already, this is a non-commutative group action, which limits what we can do with it. For C side, you have this commutative group action, which allows you to do key exchange, for example. But I think this is a much faster group action. So for signatures, it actually makes sense to also consider this the non-commutative group actions. Or if you're very clever, maybe you can make it into a commutative group action. I tried to, I didn't manage to solve it, but if you know how to, please let me know. So let's make a zero knowledge interactive proof of knowledge just from these group actions, right? So we have our secret key is just a group action element G, and then we can give a starting point x0, and then our public key is basically x1, you could say. And then we assume that nobody can find G from this. Then we commit to some x prime. Again, we just pick a random group element and apply it. And then we can also compute G1 as the composition of these two. And then the prover commits to this x prime. And then the verifier is just going to pick either 0 or 1, sends it back. And then we can easily say, oh, if it was a 0, we'll send back G0. And if it was a 1, we'll send back G1, of course. You all know this, but if you write it down in cryptographic group actions, you also immediately see how easy this would be to adapt to other primitives that you would want to make. And that's actually all that I wanted to tell already. So we can go to the coffee break again really quickly. But to summarize, what I really want to say is that I'm advertising matrix code equivalence here. So this is a cryptographic primitive that's actually quite easy to understand. It's just these maps between these matrix codes. And the complexity is linked to this problem in multivariate crypto, this isomorphism of these polynomials. This is already quite well studied. And then it makes a cryptographic group action, which is a great building block. And if this doesn't convince you yet to start using matrix code equivalence, understanding these equivalences mathematically is also a very interesting part of coding theory, where you have a lot of challenges that we haven't solved yet. And with that, I want to thank you all for listening. And if you have any questions, feel free to ask.
Thank you, Krijn.
So you said you tried to pick a commutative sample. What did you try? And what happens if you pick a random, diagonal, do something with diagonal matrices?
Yeah, it's hard to prove that it's still as secure, because you don't really know the set of equivalent codes that you get then, and you also don't know if this. So it's, for example, on a high level, the problem in C side is that it's a commutative cryptographic group action, and then you have it you can map it as a hidden abelian shift problem. And then you have improved quantum attacks, and you have to expand the whole thing, and then it got horribly so slow. I haven't looked at this in detail, but clearly this should also apply here. If you make it into a commutative proof action, it should. This should happen, right? And then does it explode or not? I don't know. But pick a random subgroup, and you're also limiting the size of these isometries already. So you have to expand the parameters there, and there it's also becoming less efficient. So all of these ideas. So for example, taking the diagonals sounds like a good first idea, but then you look a bit deeper into it, and it doesn't seem to really work out. So I don't know if it can actually be done. It's tricky.
There is this new competency class called tensors of TI, and there are also TI complete problems, and this seems not the complete problems. Do you know about them?
This is a very good question to ask at Eurocrypt. There's a talk there on this trilinear forms, and I think they link as well. Indeed, they say that the quadratic map's linear equivalence is a TI complete problem, and then with the equivalence, you would say, well, then this is also equivalent to that. So I think my guess would be yes, but I don't know the theory behind this paper in detail.
I have a very quick question for Krijn, actually. So I can certainly relate to the mathematical beauty of the theory, and I agree 100%. But maybe on a nitty-gritty perspective, you can maybe comment quickly about the practical as well of this, because of course, when like, how does this relate to the Hamming case, right? To the rest, and do you have any idea?
Yeah. So for probably key sizes or for signature sizes, I think you get smaller signature sizes if you would do this than compared to less of them. So that's good. With regards to speed, I don't know actually. I don't know that there's no real implementation yet. You can get the theoretical numbers for signature sizes easily, but then to figure out how fast it would be, I have no idea. But it's just easy matrix multiplication, so it shouldn't be too slow.
So it's promising in the sense.
It's in that sense it's promising. Yeah, definitely.
Not. Thank you, Krijn, again for the talk.